Hello everyone, in this video we're going to be discussing section 5.2 using perpendicular bisectors. Alright, so I've got two chunks there that I need to delve into, and that's the perpendicular piece and the bisector piece. Alright, so in lesson 1.3 we learned that a segment bisector intersects a segment at a midpoint. Alright, it could be a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint, and that's going to be called the perpendicular bisector. Alright, and a point is equidistant from the two figures if it is the same distance from each figure. Alright, so points on the perpendicular bisector are equidistant from the segment's endpoints. That would definitely be a good note to take down. Alright, points on the perpendicular bisector, any point on the perpendicular bisector are going to be equidistant from the segment's endpoints. So for example, point C right there is on the perpendicular bisector, CP. So that means that I'm going to be equidistant from A than I am from B, equal distance. Alright, so I've got two theorems here, theorem 5.2, the perpendicular bisector theorem. And then I have its converse. So in a plane, because we are in Euclidean geometry, so we're pretty much messing on flat surfaces here. Alright, if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. Okay, so first I've got to know that CP is the perpendicular bisector. So if CP is the perpendicular bisector of segment AB, then CA is congruent to CB. Alright, but first I have to have the perpendicular bisector piece. And then the converse of that, if you remember what a converse does, it swaps your hypothesis and conclusion. In a plane, if a point is equidistant from the endpoints of a segment, then that point is going to lie on the perpendicular bisector of the segment. So here I am given that DA is congruent to DB, so it's equidistant to the endpoints of a segment. So that means that D is going to lie on the perpendicular bisector. Alright, if I extend it, I can see that it does. So we're going to use those to basically set some stuff equal. Line BD is the perpendicular bisector of AC. Alright, that's fantastic. Since that is the information that I am given, I want to go ahead and draw in its perpendicular and its bisector. Alright, I've got to have that. So find AD. Alright, now I'm going to go through a couple of additional steps if you forgot about the theorem. And if you forgot about that theorem saying that you can set DC equal to DA, you actually have congruent triangles here. So they have a shared side. So by side angle side, or since it's right triangles, leg leg, right, we can prove those two triangles congruent. Since those two triangles are congruent, I know that their hypotenuse are congruent. So shortcutting it with the perpendicular bisector theorem, I know that AD is supposed to equal CD. So I have 5x equal to 3x plus 14, and that would give me 2x equals 14 in between there stepwise, x equals 7. Alright, congrats, you found x. However, the problem asks for AD. Keep in mind, in geometry, they love to do that. So don't just find x, actually read your problem. So I need to substitute that back in and find AD, having a length of 35. Alright, here in example 2, we have got this diagram where WX, line WX, is the perpendicular bisector of segment YZ. So I have the perpendicular piece drawn in there. Let's go ahead and get the bisector drawn in. Alright, what segment lengths in the diagram are equal? And then is V on WX? x. Alright, so I've got some segment lengths that should be equal since I have a perpendicular bisector. So, wx bisects yz. So we've got to know that xy is congruent or equal to xz. Alright, and because w is given to us, right, since w is on the perpendicular bisector, we know that wy is going to also be equidistant to the endpoints of the segment. So wy is equal to wz. And then we also know that since these distances up top are equal, v is going to fall on the mid-segment as well. Alright, so we also know those two segments are equal. So is v on wx, just kind of touched on that? Yes, absolutely. Since it is equidistant to the endpoints of the segment, I know that it falls on the perpendicular bisector by the converse. Alright, so here's a couple guided practice problems. Read through them, pause the video, see if you can answer them on your own, and then a solution will pop up in a second. Alright, so let's talk about concurrency. So in the next several sections, we are going to be talking about different concurrent points. Okay, so when three or more lines, rays, or segments intersect at the same point, they are called concurrent lines, rays, or segments. So their point of intersection is called the point of concurrency. So I can have different types of lines, right, that are all going to intersect. So the different types of lines or rays or segments that I'm talking about are, for example, in this section, we're talking about perpendicular bisectors. So they have some requirements, right, in order to draw them. I need them to be perpendicular and I need them to bisect. In the next couple of sections, we're going to talk about angle bisectors and medians and altitudes, right? Those all have different requirements in order for me to draw those in there. They have different definitions. So, regardless, let's say here I have three different lines, all right, or segments. I have them all intersecting at the same point. That's going to be called the point of concurrency. Alright, so here, the concurrency of perpendicular bisectors. So, the very first thing that I'm going to want to do is draw myself a nice triangle, and then I need perpendicular bisectors. So, here I've got DP, EP, and FP. They are perpendicular bisectors. Alright, so I'm going to draw in all of that information. That's what I'm starting with. It says that the perpendicular bisectors intersect at a point that is equidistant to the vertices. Alright, so here I can see that I've got a perpendicular bisector to every single side, and they are all going to intersect at one point, P, and what this actually ends up telling us, and you can see it in red, that BP, AP, and CP are all congruent. Right? It's just this one little funny, fact, or it can be proven. Alright, we're not going to go through the proof of it. We're just going to use the information. So if I've got perpendicular bisectors, I know that from that point of concurrency out to the vertex, each vertex, it is going to be equal in length. Alright, so example 3, frozen yogurt. 3 snack carts sell frozen yogurts at points A, B, and C outside of the city. each of the 3 cards is the same distance. It's saying that it's the same distance. So this is congruent to this, is congruent to this. Find the location for the distributor that is equidistant from the 3 cards. So, here in using theorem 5.4, it shows us that you can find a point that's equidistant from the 3 points by using the perpendicular bisectors, right? So if I use that theorem and I draw in my perpendicular bisectors, making sure that it's equidistant to the vertices, I know that by definition that optimal point for the factory is going to be, or the distributor is going to be the point of concurrency that I'm going to label D. Alright, so here's a guided practice problem. What if hot pretzels are sold from points A and B, and also from a cart at point E? Where could the pretzel distributor be if it is equidistant from those 3 points? So sketch the triangle and show the location. Alright, and hopefully you're drawing your perpendicular bisectors there and seeing where the point of concurrency is. Alright, so we're going to use this point of concurrency with our perpendicular bisectors to form this definition. So the point of concurrency of the 3 perpendicular bisectors of a triangle actually has a name. It is a point of concurrency, however we have multiple types of points of concurrency. This one's called a circumcenter. A circumcenter. Alright, the circumcenter P is equidistant. Alright, so if you were to remember circumcenter P, circumcenter is equidistant from the vertices. Circumcenter is equidistant from the vertices, perpendicular bisectors. Alright, those 3 pieces of information need to go together. Alright, so P, my circumcenter, is going to be the center of a circle that passes through all 3 vertices. Alright, so since it is, I'm going to draw in my lines here, since here's my point of concurrency, it's equidistant, alright, to each of my vertices. I'm drawing all of that in there. It's equidistant, so you should see those segments are all equal, all the green ones. Alright, that actually is going to form a radius. Alright, so if it's equidistant to each of the vertices, I can put a pin down on my circumcenter, take a piece of string, and circle it around my triangle. Alright, if I take the string and go to one vertex and then I circle that around, maintaining the same distance, I'm actually going to hit every single vertex on all of these triangles. Alright, now, breaking down what the word circumcenter means, alright, that means to go around. If you think about circumnavigate, circumference, we've talked about circumference, that's the length around a circle, the distance around a circle. Circumscribe means to draw around something. Circumvent, sometimes you have to circumvent a situation if you're working around different people. Alright, that's kind of like skipping your boss and going to your boss's boss. Alright, so depending on the type of triangle we have, here we have an example of an acute, a right, and obtuse triangle. Analyzing it according to the different angles, I've got different locations in which my point of concurrency, my circumcenter, can lie. So if it's acute and you were to draw it in there, alright, I've got my perpendicular bisector of every single side, you would see, and for the record, if you're just trying to sketch it out and see, okay, is it supposed to be inside or outside, you're only going to need to draw in the perpendicular bisectors of 2 of the sides. because wherever those intersect, that's where the third one's going to intersect as well. All right, so for an acute triangle, it's going to be inside. For a right triangle, the circumcenter is going to be on the triangle. And then for an obtuse triangle, it's going to be outside of the triangle. Now, these are pieces of information that I have never memorized. All right, what I have memorized is that the circumcenter goes with perpendicular bisectors, and then from there, from my drawing, if I draw the perpendicular bisectors in, I can draw in all those lines and I can see that it's equidistant to the vertices. All right, and then I can draw in a circle. Alright, so you're going to be using that on your homework. So if you guys have any questions, feel free to send me an email, and I look forward to hearing from you. Good luck and good hunting.